Okay, bear with me. So this next video, it's long, it's cheaty, it's notes, it's problems out of the book, but we have to go through. So if we let's apply some rules, some problems. So if we let x equal log base 10 of a, and we let y equals log base 10 of b, the first thing you might be asked to expand log base of 10, 100 a squared over b. And so when we're asked to expand something, you say, okay, here's division. So it's log base 10 of 100 a squared minus log base 10 of b. And then right here you see multiplication. So you have log base 10 of 100 plus log base 10 of a squared minus log base 10 of b. We might want to expand even further. You say, oh look, there's an exponent up there. So I can do log, so let's deal with that first. Log, so we have 2 log base 10 of a minus log 10 of b. And then I look over here and I say, oh wait, I can simplify this. Log base 10 of 10, well, you either know that by instinct because of Ben, it's like 10 to the second equals 100, or from the last lesson, we can rewrite 100 as 10 squared, so we know this is 2. And then finally, since we said that log base 10 of a is x, and log base 10 of b is y, we can simplify this as 2 plus 2x minus y. We have to go through it. It's tedious. Next example. Expand log base 10 of the square root of a minus b. You could do, there's 100 different ways to do this. You might say, okay, I'm going to rewrite this as log base 10 of a minus b to the 1/2. You might put the 1/2 in front, and then subtract log base 10 of a minus log base 10 of b, and so you have 1/2 x minus y. You could have done the 1/2 to both the brackets. So you can do 1/2 to the a, 1/2 to the b. It's up to you, but this is the idea of expansion. If we can expand it out, then we can pull it back together. In this next example, I'm erasing this. In this next example, right, we have log, sorry, let me erase this, I apologize. So in this next example, we have the log base 2 of x plus log base 2 of x plus 4 equals 5. Okay? So once again, if we can expand this out, we can also use the rules to smush everything together. Well, we have addition and we have logarithm with the same base. So I'm going to bring this together. Log base 2 of x squared plus 4x equals 5. All right, does everyone see what I did? I multiplied x times x plus 4. Then what I can do is turn this into an exponent. I can undo this and make this bend. Use bend. Get it out of log world. Go into exponents. And you see, okay, you know what? 2 to the, x squared. Well, Ben says 2 to the 5th equals x squared plus 4x. So this is x squared plus 4x minus 32 equals 0. And then we have a quadratic. Let's talk about this because I did talk about something with my log graphs I need to mention. So we see here we have x plus 8, x minus 4 equals 0, and we have two solutions. X equals negative 8 and x equals 4. Now, if this were disconnected from anything, these would be two valid solutions, but they're not. And so what we see here is that when we put the -8 back in the logarithms, right, we have a negative number. Now, what I did talk about in the video is that if, sorry, let me just quickly talk about this now. That's why, once again, when we saw the exponential, well, this is good, we have base 2. With the exponential, the domain is all reals, but the range is y is greater than 0. Well, sorry, this is y equals 2 to the x. Well, that would mean that the inverse, or the logarithm, right, remember, the domain of the function is the range of the inverse, and that means the range of the function is the domain of the range of the function is the domain of the inverse. So when we're doing logarithms, when we're looking at logarithms, you can only have positive numbers in here. So we can't have that. This goes. So you have to check your solutions. Am I putting in negative numbers in my logarithms? We can't have that. You will be able to have this when you go to college and you study complex analysis and complex numbers, but in this class, logarithms are in the real world, you can have negative numbers in here. That might be something to explore for your exploration, complex numbers, right? So, x equals 4. Okay. Now, the next thing we have to talk about is something called change of base. And this is awesome. I love, love, love this. Let's see. This is I love this. I'm sorry, I have to say it again. Change of base. You can change the base. This is really cool. If you have log base b with a, you can rewrite this as take the a, right, and then take the b and put it in the denominator. You ready for this? You can choose any base you want. That's awesome, right? So this makes your life much easier, right? So if we see log base 9 of 27, and you don't want to deal with the fractions because like you're just not in the mood, you can rewrite both of these as, you can say log of 27 over log of 9, and you know what base I'm going to choose? What do you think? 3. Yes, I love this. So 3 to what power gives me 27, and 3 to what power gives me 9? That's the fast way to do it. It's really amazing. What's the proof? What's the proof? How do we prove this, actually? Let's not log. So what's the proof? I'm not going to ask you to prove this, but I'm going to show you. Let's start with log of b, and let's call that x. Right? So that means if I take it out of log world and go in exponential world, this becomes b to the x equals a, right? Now, if a rule that we did talk about, I guess I didn't bring it up. I guess if I do something to the left, I have to do to the right. So you know what? I guess I can take the log of c to both sides. Once again, if you do something to the left, you do it to the right. And then we see that our power rule, x log base c b equals log base c of a, and then finally we get the proof at, this is the idea of change of base. Once again, why do you need change of base? Because your calculator was, so why do we need this? Once again, this is something it's like old school. If you look at your calculator, you have log of base 10 and log with base e. And so if you looked at this problem, log of 927, you had to use your calculator, the tables, you had to change it into log of 27 divided by log of 9. So you go to your scientific calculator, which had log and ln on, and you're able to do this. But your calculators can actually do this. And you can see that. So, that really takes it. We're teaching this, I'm talking about this, but the technology can do this for you. So we don't need all of this. But you need it because you have to solve problems like this on the IB exam. Log base 3 of x plus log base 9 of x equals 2. So what are you going to do here? Well, you think, well, there's log rules, I can combine them, but the problem is you can't because these bases are not the same. Any suggestions? Change of base. The second you see different bases, change of base. Sorry. Change everything to the lower base. Change everything to the lower base. So I'm gonna keep log base 3 of 9, but I'm gonna do log base 3 of x over log base 3 of 9 equals 2. Well, these problems they're probably part 1 questions if they show up, and they nicely work out. So you have log base 3 of x plus, what's log base 3 of 9? It's 2. So we have 1/2 log base 3 of x equals 2. And you see it works out. So it's 3 over 2 log base 3 of x equals 2. Log base 3, how are we doing? What is this? Log base 3 of x equals 4/3. Therefore, x equals 3 to the 4/3. You would leave it like that. And these problems show up like this. In your notebook, prove this. This is kind of cool. Log base a of b is equal to 1 over log base b of n. Try that out and talk to each other. The last thing we have to do, sorry, I told you this was not tedious. We have to be able to solve problems. You might see, you're going to see them because I'm going to give you them. You might see problems like this, like 5 times 2 to the x equals 3 times, 7 to the x. You're going to see something like this. We are with constants and bases and exponents. The goal is rewrite. You're going to rewrite as, b to the x equals c, and then you're going to have to use your GDC. So the question is, how do I transform this? It's easy. It's easy. Just divide both sides by 7x to the x, and then divide both sides by 5. So you have 2/7 x equals 3/5. GDC problem. Once again, don't get weirded out. It's just algebraic manipulation. But once again, you're just manipulating. let's look at another one. One last one. You literally could just make these up, like, 5 times 5 to the 2x equals 7 times 3x minus 1. How do you deal with this? Well, I'm going to rewrite this as 5 times 2x plus 1 equals 7 times 3x minus 1. What other manipulation can I do? You know what? This is 5 times 25x. Well, actually, no, sorry. What do you think? Well, actually, I shouldn't have done this. Let's just leave it like this. Let's rewrite this as 5 times 25 to the x. And let's change this to over 3. So I have 25x over 3 to the x equals 7 over 15. 25 over 3 to the x equals 7 over 15. All I did was just manipulate this so I have it in the form of b to the x equals c. That's basically it. I'll put some homework problems up. You'll have a week to do all this stuff. It's kind of fun. Okay.